So here's where we left off last time. We found that the answer for number 9 was negative 426,504 voltage, but as you can see from this, it turns out there's like a lot of work behind it. We can kind of shorten this problem by first finding the voltage of each one. So if we look at the problem again, except this time we're going to use voltage instead of finding the electric field. So each charge, we learned, is going to exert an electric field or a volt on that point P. The electric field is equal to kq over r squared, and we said that the volt is equal to negative E times D, and E is, so it's negative kqr squared times D. Now D and R both represent the distance from the charge and the actual place being affected are the same, so when we get that, we get negative kqr squared times R, so basically a simplified version of our equation is kq over R negative is equal to the voltage. Now, and the problem with the last problem is the electric field is a vector, so we have to break it up into its x and y components and do all this stuff that takes a long time. But voltage, though, voltage is a scalar. It's made up of joules per coulomb. Joules is a scalar, coulomb's a scalar. If we look at the other equation, V equals negative E times D, E, the electric field, is a vector. D stands for displacement, which is also a vector, and we kind of got ahead of ourselves here. And since E and D are both vectors, when we multiply two vectors, what we get is a scalar. So both equations show us that volts or potential difference is a scalar, which is good, especially when we're trying to find them and add them all up together. So basically, since volts is a scalar, we're happy because we don't have to do any extra trig when adding. So what we do, instead of finding the electric field of each one, we find the volts. So we look at V1 created by that 8 microcoulomb charge. So we do the whole thing. We use that equation we derive, kq divided by r, and we get our voltage. Then we do the same thing for V2. We do 8.99 times 10 to the 9th kq over r, and we get negative 359,600 joules per coulomb, which is the same thing as, negative 359,600 volts. And then we still have to do our R3. We have to figure out what the distance between the negative 12 microcoulombs and P is. And once we figure that out, we can plug in that number, which is 0.4, into our equation and solve for V3. Now, again, the whole reason that this is a much easier way is because voltage is not a vector, it's a scalar. So when we try to find the net voltage, we can just add them all up. We just add up our different voltages, a positive, a negative, we plug it in, and we get our answer. The net voltage felt at that point is negative 423,814. Now in our last problem, we got negative 426,000 instead of negative 423,000. Now, it sounds like a lot, but it's really, really small difference when you think of it, and a lot of it comes down to rounding. So this is the easier way to kind of figure that out.